Hello again to my YouTube channel. Today in this classroom, I will discuss with you one of the famous algorithms we have in machine learning and in data science is decision tree. Well, I will show you directly how it's work and what is the math behind the decision tree and what is the purpose or which kind of problem we can solve using decision tree. Well, as we see with me in this screenshot, the decision tree classifier and decision tree regression. That means the decision tree, the first idea we can have here based on this first sentence is the decision tree, we can use it in a classification problem and a regression problem. That means the first type of machine learning is the supervised machine learning. Well, decision tree help us or help to solving the classification problem and the regression problem. That means if we have some categories to classify something, or if we have the continuous values based on some features, we can predict the next or the future values. Well, what is exactly decision tree? So we can just say decision tree has a nested if-else clause. That means if we try to translate uh, this algorithms of decision tree, how it's work, if we want to apply the classical way or the classical approach we have in programming languages, we can just see is a lot of instruction with if clause, uh, if clause instruction or if clause keywords. Well, if so, I will show you for examples. Okay, based on the age of person. Well, so this example show for us how the algorithm of decision tree work. Well, if we consider this example based on the age of person, so the first condition here, if the person age is less than 20 to 21 years old, that means we need to print this. He should be in college. Elif or else if or elif. So because we're using here Python, well, we inspired from we are taking the blueprint of Python. It's okay. Well, we have elif person age is more or equal to 21 years old, and the person age is less or equal to 13 years old. That means we need to print or we should be in the working. So if we have age between the range of this age of 21 and 13 should be in working. If that means if we have some person with more or equal to 13 and the person less or equal to 13.5 or 35, sorry, we should be in business. If we don't have any condition verified here with this instruction, we will go to out of the program and print its retired. Okay, so this is idea or this is the syntax or how we have this small example show for us how this entry work. Well, if we try to translate it to like tree with a node, so we have here this first node is if we have the age, it's less than 21 years old. If yes, we go to college. If no, we should verify our value. That means we see if this range or this value of age it's between 21 and 13. At this time, we need to check it here if this value is existing this range of age. If not, we go again to check. If yes, we go to working. Well, if no, that means we need to check in again. The value of age is between 13 or 35. If yes, we go to business. If no, it's retired. So this is how the decision tree work, and also we can use this kind of thinking to solving our real problem in the life. This algorithm is efficient algorithm. Well, we will try to create this kind of decision tree with respective to classification or regression problem. As I told you before, the decision tree, we can use it both problems with the classification and the regression problem. So in decision tree are two types of techniques. So that's mean inside of this decision tree we have two techniques. The first one is ED tree, that's mean iterative dichotomy tree algorithms, and the second one is CART, that's mean classification and regression tree. So for EDE tree and CART, we'll be having almost the same functionality. That means we do the same things, the same things. Okay, we can solve in the same problem both using these two techniques. And CART always leads to binary classification. That means the CART, this CART we use it, we have binary classification. That means we have just two categories. Yes, no, red, black. That means two values, just two values. Okay. Well, in ED3, we are not leads to binary classification. That means ED3, we cannot use it to solving this kind of problem of binary classification. Well, if we take in this example here, I will show you that's how it works. If we take in this small dataset we have here, we have outlook, we have temperature, we have humidity, we have wind and brightness. Well, this is all values we have in this outlook. Sunny, we have overcast, and we have run. We have just three values duplicated in this feature of outlook. We have also this temperature, we have hot, mild, cold. Well, we have also these three values. Also in humidity, we have high, normal. Okay, well, it's checking. We have high and normal, just two values. Also in wind, we have weak, strong, weak, strong. Well, it's both values replicated here in this wind feature. Also, the target variable or the target feature here is lighting. That means we can, based on these four feature we have here, we cannot predict if lighting is or not. Here is the classification problem, especially it's binary classification problem because we have just two answers, yes or not. Well, let's continue here to see. So this is the table we have, content all the value, the available data we have. So if we go here, we are trying to simplify all these things more. So let's take an Outlook feature here. As I showed you before, we have all these features. We want to start with Outlook feature. Okay, here in this example, just to build in demonstration based on this small data set we have. So if we are starting with the Outlook feature, so unique categories are three. That means we have just three values and duplicated here in this feature. We have sunny and we have overcast and we have run. Well, if we starting with this feature, that means Outlook, we have 9 yes and 5 no. Well, if we go here, how we get this value? If we go to this table again, well, if we check here, we have okay. If we check here the predicted values here, well, we count in our number of no here. We have no 1, 2, 3, and 4, and 5. And for yes, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, this value here we get it based on the target feature we have. That means play the tennis. Well, this is all the available data we have. The outlook is go here to sunny based on this outlook. So because outlook it's counting just three values. We have sunny, overcast, and the run. So the first one here is the sunny. We need again to count how number of the predicted of yes and no we have based on the sunny. If we go to our table again here, if we go to sunny, sunny here we have no, sunny again here, the outlook and the target or is the value here is no. Okay, and if we go again here sunny also we have no. This that means we have three no's, three no, and we have also here sunny. We have the first yes, and sunny again here yes. That means 2 yes and 3 no. Okay, based on this value of sunny, we have 2 yes and 3 no. Also for overcast, we have 4 yes and 0 no. If we check again here to go to this value of overcast, we have the overcast here, yes. Overcast again here, we have yes value. Overcast again, we have yes. And the last one here, overcast, we have yes. That means we have 4 yes and 0 no. Okay, and this, if we have this scenario, that's what's called leaf node. Okay, because we have only one values in this case. We have 4 yes and 0 no. Okay, well, if we continue the process, if we go to the run value, we have also 3 yes and 2 no. If we check in here for run here we have no, first no. Run here we go, we have yes. So we have, sorry, we have also here run, we have no value, run yes, and the run yes. That means we have 3 yes and 2 no. Okay, so this things happen here. We are starting with this outlook feature, and we have 3 values duplicated, and we dividing the values of the targeted answers here based on this all possible value we have here in this outlook feature. Here we have leaf node means should, so either it should be yes or it should be no. That means the leaf node here we stop here, so we cannot be split more or to extract more information based on these answers we have. So we stop here because we have 4 yes and 0 no. We don't have any other values here without 0 4 no. That means we stop here because we have just yes no. Okay. Um, so the example we have here for leaf node, we have 4 yes and 0 no. That means we cannot continue. Also the search or the inverse, it's work also. If we have 0 yes and 4 no, it's still also a leaf node. The further splitting will happen with respectively sunny and run. That means we we can also split or continue to drawing this tree based on sunny and run. Because why? Why? Because we have also some values here for yes and no, both in this run and sunny. But for overcast, we stop here. That's what's called the leaf node. Overcast splitting will not be happen. Splitting will be unless and until we don't get the leaf node. That means here for the sunny and run, we continue the process of drawing this tree, the tree until finding the leaf node. But here for the overcast, it will not be happen. Well, to check whether overcast is leaf node or not, there are two terms. The first one is the purity. Here, how we can know some node is a leaf or not? Based on this concept of purity here, we start the first one, the purity. The purity means the decision tree is going to check in whether the tree appears split or not. So based on this purity, these algorithms, it will be checking this node, it will be split or not. Well, to check pure split or not, we have two main things. We have entropy and Gini index. That means we have two methods, two techniques here in the purity to check in this if this leaf is a leaf node or not. We have the entropy and we have Gini index. Well, we go there. How the feature all selected? Of course, for this we have a technique called information gain. That means if we using the algorithm of decision tree to solving a problem of classification and regression, sorry, the feature that will be selected is not randomly. We need some technique or some approach to use it based on the information provided. We can select in some feature. This process is not happen randomly. Well, to using the feature based on the dataset we have, we need information gain. Well, if we turn to the purity, if we starting with the ontropy function in the purity, we use it in binary classification and multi-class classification. Binary classification, that's mean we have just two class, and in multi-classification we have more than two class. In case of binary classification, is easy one here. The formula, we have the entropy equal to minus p minus probability for the plus class log 2, this means logarithm of base 2 for this probability minus the probability of the 1 or the 0 class. So if we consider this 0 and 1 or 1 and 0, that means we have here 1 class and here 0 class plus log 2 probability or log 2 probability of the class 1 minus 0 class minus log of this probability of 0 class, because this is probability. If there are three categories, C1 plus or C2 or C3, at this time, this formula of this entropy is coming like that. Well, I will show you how. So if we have more than one class at this time, well, we have minus probability of class 1 log 2. Okay, probability of class 1 log 2, probability of class 1 minus probability of class 2 time logarithm 2 or base 2 for logarithm 2 minus probability of class 3 logarithm to class 3. This is the formula. How does it work? So this formula it work in case of three class, and this is for if we have just two class binary classification problem. That means probability of class 1 times logarithm of probability of class 1 minus probability of class 2 minus logarithm 2 for probability for class 2. This is the formula of entropy. Well, if we take in this example here, feature 1, so if we consider this feature 1, we have here 3 yes and 3 no based on our dataset. So this feature is split into two. For class 1, we have 3 yes and 3 no. That means 50%, 50%. And for class 2, we have 2 yes and 0 no. Here is leaf node because we have 0 no here. We cannot extract more information based on this class 2. Well, the process can be continue in this class 1. So how to calculate the entropy of C1 and C2? It's easy. Just we take in here as we see. So for class 1, if we start in with this class, okay, I will circle here. Well, for class 1, so the entropy of this class equal to minus 3 divided by 6. How we get this value? So 3 plus 3 is 6, and if we take in this first one here is yes, that means 3 divided by the total, 3 divided by 6. Well, we have here minus 3 divided by 6 times log 2 of 3 divided by 6. That means the probability minus 3 divided by 6 again, because the 3 no, divided by 6, 3 divided by 6 log 2 log 3 divided by 6. How we calculate the entropy. So here in this case we get 0, we get 1. Okay, if we calculate in here this value, we get 0. So that's mean very impure split. For 3 yes and 3 no, we have 50%, 50%, because we have 3 So we replace the probability for each class here, and we get 1. In this case, that means we have the very impure split. And for class 2, how we get, so the same things, we replace the value in each part of this equation or this fraction. You have minus 3 by 3. Why? Because 3 plus 0, here we get 3 plus 0 is 3. That means if we start in with 3, yes, that means it's 3 divided by 3. Well, if we continue here, we have minus 3 divided by 3 log 2 of 3 divided by 3 minus 0 divided by 3, because the 0 here for now is not exist. We have 0 divided by 3 times log 2 of 0 divided by 3 and equal 0 minus 0, because here 3 by 3 is 1, 1 times 0 here, because here is 3 divided by 3 is 0. Well, the 0 minus 0 is equal to 0. This is pure split. That means it's leaf node. We cannot continue. So becoming getting a leaf node here, either yes or either not. That means we have the leaf node here, or we are stopping the process here if we get 0 for yes or no. Here, if we take in another example here, if we consider we have 2 yes and 3 no, what happens if we can place the same values, or we replacing those values here in this equation, we get 2 divided by 5, because 2 plus 3 is 5. That means we have no, we have 2 yes and 3 no. It's minus 2 divided by 5 log 2 of 2 divided by 5 minus 3 divided by 5, because 3 of no here, 3 divided by 5 log of 2, 3 by 5. And the result here is 0.97. Is impure split. Okay, this is impure split here. So whenever we get here, just we have some observation. So whenever we get a leaf node, it's a pure split. That means if we have a leaf node here, that means in this case of problem we have binary classification. If we get 0 yes or 0 no, that means it's a leaf node. At this time, it's considered like a pure split. Whenever we get some number of yes and some number of no, that means it's impure split. That means we can extract more information behind this node. Well, if we take in this curve here, as we see, we have in the x-axis here, we have the range of values between 0 and 1 is probability of class 1. And if we look here, we have 0.5, that's mean the middle point. Okay, we have the middle point here. Well, if we look in this observation, we have 0.5 in 3 yes and 3 no. That means we have the equal values here. We have equal values. We have 3 by 6, it's 1550. Entropy, in this case value, it will be 1. That's what we got before. That means the max value we can get here, or the max value we can get with this entropy function is 1. When we get this value, if we have the same probability, that means we have 0.5, 0.5 for each of these value of yes or no, and no. That's what we see here. So we can get the max value here of this curve if we have 50%, 50. And the value it's described again here if we have this probability go in this sense or in this direction, we get this value of entropy go down. Well, so here, what feature we take in to split? So the second one here, we see now the entropy function, how it works. We go again to this and Gini index. So how we consider the entropy and the Gini index, just to extract the purity. Okay, the purity does mean what is the feature I will start with based on the Gini information provided. Well, if we see here the Gini index again, the formula of this Gini index is 1 minus the sum of all the probability start from 1 to n, p squared equal to 1 minus the probability of class 1 squared plus probability of minus class squared. So if we consider the category 1 here and we consider this value, we have 3 yes and 3 no. That means we need to calculate again the information based on the Gini index here. We have the same values here. We have 3 yes and 3 no. At this time, if we replace each uh, a variable here in this equation by its own value, we get 1 minus probability of class plus squared plus minus probability of the class minus squared. That's mean equal to 1 minus 1 divided by 2, because half we have 3 and we know that's mean 1 divided by 2 squared plus 1 divided by 2 squared. 1 divided by 2, that's mean it's a half, it's 0.5. Well, it's equal to 1 minus 1 divided by 2 equal to 0.5. That's mean the middle. When we get, this is the max value we can get with Gini index using this half. This is the same graph here with this Gini information here in this case. The range of values, of course, is 0, is between 0 and 1, sorry. We have here the middle value 0.5, and the max value we can get using this Gini information or Gini index, it's 0.5. So if we replace the value here, we get 0.5. This means the max value can I get using the Gini information. So whenever my plus or this class plus is 0.5 and again index, my output that it's going to come is 0.5 for an impure split. Well, so let's say in this example we have this feature, we don't know it, and we have class 1, we have 4 yes and 8 no, and for class 2 we have 8 yes and 2 no. If we consider all this value we have here in these nodes, both of nodes, class 1 and sorry, class 1 and class 2, and using this Gini index, if we replace those value here, we have 4 yes and 4 no. That means we have 1 minus 4 divided by 12, because sum 4 plus 8, it's 12. That means 4 yes divided by total is 12 squared plus 8 divided by 12 squared, 8 is 4 no. And we consider here 1 minus 0 0.111 plus 0 0.444 here. It's 1 minus 0 0.555 here. And the Gini index here, the value of Gini index is 0 0.4445. Okay. Also, the same things for 40 yes or 80 yes. We replace each value here. We have 1 minus 8 divided by 10, because 2 plus 8 is 10. 8 divided by 10 squared plus 2 divided by 10 squared is equal to 1 minus 0 0.64 plus 0 0.04. And the result here is 0 0.32. Okay. Here, as observation, Gini information or entropy, we do the same job. But the Gini index is used for large data set. That means if we are taking a large sample, at this time we can or we need to use the Gini index. But for entropy, use it for a small data set. Why we need to specify each of these technique for some conditions, or we need to associate useful or the Gini index for some for some conditions. That means in this case with large data set, because computation is expensive. If we have a large data set and use entropy, for example, the computation it will be expensive. That means the complexity it will be more complex. Which feature we take into split? Okay, at this time we can answer for this question, because as I tell you before, if we try to solve in a problem based on some dataset provided, We can not trace the features randomly. We need some technique help us to tracing some feature before trying to split it. So which feature for splitting? There are many features. In this case, as I show you, sorry, as I show you before in the table, we have four features. We have outlook, we have temperature, humidity, and we have wind. We have four features. Which one we can start with? We are particularly selected outlook, and why? We need a reason why we need trace or to start with the outlook feature. After outlook, after sunny, which attribute to take for the for the next splitting. So for the above answers, we get using information gain. That means to tracing some feature, not another one, we need information gain. We need to calculate what's called information gain. So let's see here in this feature, we have 9 yes and 5 no. If we return to first example, I start with you with, to simplify or show you how decision tree work. If we take in this feature, if one we have 9 yes and 4 now, and 5 no, sorry. Well, here if we split it to class 1, we have 6 yes and 2 no, and also for class 2, we have 3 yes and 3 no. If we calculate entropy again, we have based on this uh, node here, we have 6 yes and 2 no. If we calculate the entropy is equal to, I go directly to values, is equal to minus 6 divided by 8. Why? Because 2 plus 6 is 8. The total here is is 8 and denominator is 8. Well, is minus 6 divided by 8 log 2 or logarithm of base 2 probability of 6 divided by 8 6 because we have 6 years and minus 2 divided by 8 no we have because here we have 2 no timed logarithm base 2 of 2 divided by 8. This is for class 1. If we go to class 2, we have 3 yes and 3 no. We have also here 3 or minus 3 divided by 6 log of 3 divided by 6 minus 3 divided by log or minus 3 divided by 6 times log divided by 3 log of 3 divided by 6, sorry. At this time we get as a value 1 here for C1 because it's very impure node. Well, we calculate in here this feature. We are here for so this feature one here we calculate the entropy and we need to calculate also the Gini index. Here in this case of C1, we go directly to this categorical 2. We have 1 minus 3 divided by 6 squared plus 3 divided by 6 squared. Also, we have 0 0.25 plus 0 0.25 also is 1 minus 0 0.5 is 0 0.5. So we in this categorical 1 when we using the entropy function we get 1 and when we using gain index we get 0 0.5. So out of this to split which is good for that information gain. So here for this feature we calculate the feature here or gain information based on the entropy and index, and also for feature 2 here we have this. Well, I might using this feature 1 or feature 2 to do the split. Well, if I using this feature 1 for the split, so information gain make sure that all the possible splits that are available in it will be tried to calculate the information gain. That means we calculate all the feature here based on the index information and entropy. At this time, we go to select the information gain. information gain by combining pure split and into, or by combining the entropy or the Gini index into that. Thus mean here we calculating the entropy and the Gini index. At this time we combine both of this and we see how we can extract. I will show you now the formula of information gain. This is how it's done. So we will have seen one split in the first three, the other split in the second or the two three, out of these which are the best split. So using this technique or this the formula of this information, we have in here, we have two parameters. We have a simple and here is the feature is equal to the entropy minus the sum of all this value we have here, absolute value of SV divided by S, simple. Okay, basically mean the child node here, this is child node here. Okay, and for S it can be entropy or Gini index. In this case here we can be Gini index or Gini index, sorry, or the entropy. So for now here is the broad entropy is considered as entropy. So for now here is each is it's considered a broad entropy. So everything is easy really here. It's not complicated. As we see, we have just a formula and we need just to understand the process how it's done. Why we why why this two decision is important, because in technique of Voisin and Bagin, one of useful technique here kind of get in the world of data science or machine learning. We kind of face in random forest or easy boost or light boost or all these algorithms work with this decision tree, because inside of all these algorithms kind of found, sorry, this tree decision is considered like a weak learner. Well, for this reason we need to understand how all these things work. Well, so for Gini information, so this is the formula here, and we need just to replace each value for inside of the formula or an equation. So if we go here for this one, for if one here, we have 9 yes and 5 no. Go to this for categorical one, we have 6 yes and 2 no. For category 2, we have 2 yes or 3 yes, 3 no. Is called child node. This is the child node here, and this is the word entropy, the feature. Uh, if we calculate the root entropy for this feature, we have minus 9 divided by 40. Why? Because 9 plus 5 is 40. This is the total for this feature. This is we calculating now the entropy or the root entropy. 9 over minus 9 divided by 40 log 2 of 9 divided by 40 minus 5 divided by 40, because we have 5 no, log 2 of 4 divided by 14 is equal to 0.94. This is the root entropy. So the entropy of this root is 0.5. Okay, we calculating now. The process or the step one is to calculating the root entropy, and based on this example we have here, we found 0.94. If we continue here for this H1, HC1 or HC category 1, we have 6 yes and 2 no. We have minus 6 divided by 8, 6 divided by total of 2 plus 6 is 8. Log 2 of 6 divided by 8 minus log or minus 2 divided by 8. Log 2 of 2 divided by 8 is equal to 0.81. Okay, this is for child node 1 here. As I show you here. Calculate now the entropy for this child node. So we go now for this one and see what we get. We have 3 yes, 3 no is minus 3 divided by 6 log 2 of 3 divided by 6 minus 3 divided by 6 log 2 of log of 3 divided by 6 equal to 1. Well, if we go here in this information or this equation of information gain, the root entropy is 0.5 or 0.45, 95, sorry, 0.94 minus 0 or 8 divided by 40. How we get this value? If we return here for these three, we have here 0 or 2 plus 6 is 8, and here 5 plus 9 is 14. That means 8 divided by 14. This is the first one. That's what we go. That's what we do here. 0 or 8 divided by 40 times 0.1 for this is the entropy for the childhood 1 times 6 divided by 40 times 1 because here 1 is the entropy of childhood, and 6 divided by 4 because 3 plus 3 is 6. 6 divided by 4, this is what we get here. 0.94 minus 0.462 plus 0.42 is equal to 0.049. This is for gain. Till we have here one split, we can go into making one more split. If two, we have 9 years for no, we have 5 years and 1 no for C1 and 4 years for no for C2. So we have this value, that means we can make more split. If we go to feature 2, the broad entropy, again here we have this value, we replace it here, we get this is the root. Okay, this is the root entropy. I will replace the same things here because we have the same value. We have 6 years and 5 now. This is 40. Replace each value here and we get 0.94. So in this case, the root entropy is 0.94. And now we need to find out child node, which is yes, I load here absolute value of is V, and for root entropy, we replace each value here. It's on because here, if we look in this example, we have for 5 years. That means we have 5 divided by 6 because 5 plus 1 is 6. That means 5 years it's 5 divided by 6. Log 2 of 5 divided by 6 minus 1 divided by 6 because we have 1 now, and the total of 5 years and 1 now is 6. That means minus 1 divided by 6 log 2 of 1 divided by 6 equal to 0.665, okay, or 65, sorry. Here for this child entropy we get 1 again because we have 4 years and 4 now, okay, and for gain if we replace it we get 0.05 because here we have the root entropy and we have here 6 divided by 4, 40 times 0, 65 minus 8 divided by 14 times 1. So each value here is all these things is clear. Here we have 6 divided by 14. Why? If we look in this example, we have here 5 plus 1 is 6. 6 divided by 9 plus 5 is 14. That means we have 6 divided by 14. Okay, that's what we do here in this formula of linear information times this entropy of childhood, also for 8 divided by 40 times 1, and we get here for information gaining is 0.09. Well, if we go to compare which one we can start with, because what is the process here? We're taking just 2 features, but in the reality we calculating this process, we duplicate it for each feature we have in dataset. At this time we are tracing the big value. After we calculating the information gain, we tracing the big value of the information gain. At this time, this feature associated with this big value we start with in the process. Where feature 1 we have split is good or not, split 2, so if 2 split is good, we have both of values here. For feature 1 we have 0.049 and for 2 equal to 0.09. So we have, if the information gain for feature 2 is greater than information gain of feature 1, that means we start with feature 2, the process. That means we're calculating the purity based on the entropy in case of binary classification, or we can use index information also, and so on. Well, we using the select information gain for 2 because it's the big one here. If you look, okay, we have here 0.4 and we have here 0.9. That means 9 is bigger than 4. For this reason, we need to trace in this one here, feature 2, to start in our process. Well, at here I will stop in this session. I will continue in the future to making some questions about this 3D session and to try to find some answers for this question we have here in the tutorial. Happy learning for everyone again. Thank you for watching. See you again. Bye bye.